I'm glad Brian reminded me, but this one I actually forgot what I was supposed to talk about, so I was just going to like prove there's my hypothesis or something. But Brian, is this mic still turned on? I heard feedback coming from it. Should we, I just want to understand.
You can turn it down, it's a little loud.
No, this hand mic. Okay. Okay, so I think all snafus are dealt with. Yes, the topic of my series of lectures at this school is going to be geometric analytic number theory. I'm going to try to convince you over the course of my talks that that is a good piece of notation. You can agree or not. But the first thing I have to do is tell you what I mean by analytic number theory. And that's already going to be slightly idiosyncratic. What set of things I'm including under that umbrella. So what do I mean by analytic number theory for the length of these lectures? So I'm just going to give kind of a list of the sorts of problems I would like to discuss and include under this umbrella. So for instance, here's a question. How many pairs of co-prime integers in the interval 1 to n cross the interval 1 to n. So this is a box of size n squared in all, and we're asking how many of these, or what's the same, what proportion of these are relatively prime. How's the size of what I'm writing? Is that good? Okay. So a similar question, dressed up in a sort of somewhat fancier sounding way, if x is a projective variety, how many points in x of q, that is how many rational points in x, I mean we're number theorists, so this is what we really care about, right? Rational points on varieties. But I'm already revealing I'm not really an analytic number theorist by saying that. How many points in x of q of height at most n? So this is this kind of question is the topic of the so-called Archimedean conjectures, and sort of this may contain some words that not everybody in the room knows, but I'll just comment that when if the projective variety we have in mind is actually the projective line, P1, then this is a rephrased version of the first question. So when you really sort of get down to the nitty-gritty, many questions in this genre turn out to be questions that have more in common with more classical analytic number theory questions like counting co-prime integers in a box. And a lot of the developments in that area really sort of come down to sort of being strong in those traditional methods. Okay, so let me understand. I think what I'm supposed to do is now go here. Good. Okay. So the list is going to continue. So, for instance, we can ask how many primes less than or equal to n. That's certainly an absolutely central and classical and old and solved question of analytic number theory that we can all agree is analytic number theory. Here's another one, which many people in the room have thought about questions in this genre. How many totally real cubic fields? And now the basic invariant, or one of the basic invariants of a number field is this discriminant, the number that measures the amount of ramification of the number field. And we can ask how many totally real cubic fields with discriminant less than or equal to n. I feel like I should take a poll. How many people think this is a question about analytic number theory? About half. I'm not sure if the others have no opinion or vehemently deny that this is part of analytic number theory. I mean, maybe as a side note, I mean, most of the questions I'm asking, you could also describe, if you wanted, as part of arithmetic statistics. That term has its own problems, too. So if you want to conceptualize my lectures as geometric arithmetic statistics, that's also totally okay. Anyway, I have even more questions. So Here, these two questions are actually completely understood. I'll just comment that if these two questions get married and have a kid, you have a question that is actually not understood at all, which is how many totally real cubic fields with prime discriminant less than or equal to n. A very interesting question, which I think at this moment is not very well understood at all. Okay, let me give yet more. So there's a family of questions which concern what you might call the autocorrelation of Mobius, which asks the following. If I take a sum for n less than or equal to big N, so a sum in some range of the following quantity, Mobius function of n times the Mobius function of n plus 1. Okay, some of you guys know what the Mobius function is, some don't. I think this is actually one of the problems I'm going to return to and talk about in this course, so hold the thought if you want to hear more about what this function is. But it's a function that sort of, for a square free integer, it measures the parity of the number of prime factors, and all you need to know for this discussion is that it's something that's either, it's a sign, it's either 1 or minus 1, and it's 1/2 the time and negative 1/2 the time. And so if you compute this sum, the question of correlation between a Mobius function and its shift is really the question of, if those two signs were independent of each other, then the product of Mobius n and Mobius n plus 1 would also be 1/2 the time and negative 1/2 the time. Right? You could model it as the product of two random signs, which is again a random sign. And if you add up capital N random signs, you should get something pretty small. Maybe you should get something of size about root n. But I'll just comment that here's a much more modest question we could ask. We could ask, at least is there no bias? At least is this little o of capital N? I mean, the biggest this sum could be is capital N if all the signs agreed, and the correlation would just sort of be measured exactly by the size of this sum. So to say that this sum divided by n goes to 0 would be to say that the correlation between Mobius and shifted Mobius was 0. So this is part of what's called the Chalic conjectures that I'll talk about not today, but later in the course. So maybe I'll write Chalic here to give a keyword. What is the probability that a quadratic imaginary field Q adjoin root minus D, and now what am I talking about probability here? What's random? What's random is D. So D is chosen randomly in the interval, and actually my intervals, I'm mostly not going to use intervals starting from 1 in this talk, so let's start here and now. Let's take D random between n and 2n. I'll explain a little more later why those intervals are a little bit cleaner for the kinds of things we're trying to do. What is the probability that this quadratic imaginary field has class number prime to 7? So it has some class group, which is a finite abelian group. Some finite abelian groups have a z mod 7z in them, and some don't. The question is, if I take a completely random quadratic imaginary field, what's the probability that the class number is prime to 7? And by the way, I want to make very clear that even the well-definedness of this question is completely unclear. In other words, why should there be a probability? Why should it not be that somehow, in an interval of this size, the proportion of quadratic imaginary fields with class number prime to 7, maybe that wildly fluctuates and has a limb sup of 1 or a limb imp of 0 for all I know. So there's sort of an implicit conjecture that there is a limiting probability, and then you can ask what it is. And this kind of question, and actually much more general questions, I'm giving you one tiny piece of it, are the subjects of the so-called Cohen-Lenstra heuristics, which I think will be this set of heuristics, and its variants will be an actor, I think, in several, actually, of the lecture series today. And, oh, so I'm sorry, nobody told me that I've done this totally wrong. So because I haven't used this kind of projector before, I hope people will kind of make some kind of an angry mumbling noise if there's some technical problem with what I'm trying to convey. And I think this is actually the last one I'll write. I mean, I have a really long list on the, I haven't even said all the ones that are in the course notes, but here's one more. If Earth existed, okay. If n is a random square free, so it's chosen randomly from this interval, conditional on it being square free, what is the probability that there exists a totally real quintic field, K over Q, and maybe I should say, no, I think I don't need to say this actually. With discriminant n. In other words, I can look at all the totally real quintic fields with square-free discriminant and like list their discriminants in a row, and like for some square-free numbers, they may be on the list. Some of them may be on the list multiple times, in fact, for all I know. That doesn't, I mean, I do actually know that that sometimes happens, it's pretty rare. So what's the probability you're on the list that there is such a field? And I'll just comment, because I think I won't actually probably get to talk about this particular problem in this set of talks. So like as a teaser, I'll just comment that I think the answer should be e to the 1 over 120. And we can talk about why I think that is.
That's not a probability.
Oh, that's e to the minus 1 over 120. Okay, it really is e to the minus 1. I'm not just randomly, it's not like Mobius where I just randomly put a sign. Okay. It's the value at 0 of the Poisson distribution with mean 1 over 120. How about that? That I know is a probability because I know the Poisson distribution is a distribution. Okay. So, I mean, these questions obviously run a fairly large gamut, but they all have in common that I think they can, to some extent, be called analytic number theory, and certainly most of them could be called arithmetic statistics, and what they have in common for me is that I think all of these questions, in some way, there's some insight to be gleaned about them from thinking about them from the point of view of the arithmetic geometer, and that's the kind of case that I want to make over the length of this course. So, so let me say something else that these questions have in common. I just want to sort of make it clear in what sort of tone of voice we're asking these questions. Namely, we're not asking, when I say how many, I'm very rarely asking for an exact answer. So let me return to this like, very first question. So when I say, so how many is meant asymptotically for most of the things we'll talk about. So for instance, the very first question I put up, which can be phrased as what is the probability that, that a pair of random integers is co-prime, many of you guys know that the answer to this question, that it's, that it's 6 over pi squared. The reason I hesitated is because in my notes it says pi squared over 6, so for some reason I seem to have adopted the convention of taking the reciprocal of every probability on this. Okay, I don't know why I did that, but I'm just going to mark it so I remember to change it. Anyway, it's But of course, when we say that the probability that two random integers are coprime is 6 over pi squared, here's what we do not mean. We don't mean that the number of xy in this box, if we take this set of pairs, I mean, this is not literally true, right? Because this is not even an integer, so no. What we mean is something like this, that if I take a limit, as the size of the box goes to infinity to the size of the number of elements in the box, the number of integers is n squared, so if I take the reciprocal of that and then times the size of this set, that this limit should be 6 over pi squared. And essentially all of the numerical questions I asked in the first part of this talk, the sense in which they might even conceivably have an answer is this sense, that we're looking for the value of some limit. We can even ask for a little more, so I want to make sure that no is still visible. That's important. So one more, that the number of coprime guys we can ask that this was equal to 6 over pi squared times n squared plus, now what I just said is equivalent to saying this plus a little o of n squared. But we can ask for something a little stronger. We can ask for a big O of n to the 2 minus delta for delta greater than 0. So this is what's called a power-saving error term. So this is kind of an intermediate level of ambitiousness. We're not asking for an exact formula, but we're asking for a little bit more than just the value of a single limit. We're asking for a limit with some good bound on the size of the error. We're sort of just attacking that little o of n and really trying to bound it. So the nature of the question or questions that my group is going to be working on actually is very much in the spirit of like really sort of understanding these error terms and what they mean geometrically. Most of what I talk about in the lectures, I think we'll be talking about main terms. So I'm going to use this magical device, like main terms and what they mean geometrically, but there's a whole other industry of understanding what error terms like this mean from a geometric point of view. Okay. And by the way, I should say, like, I don't want to leave this as some kind of mystery. Like, this is in fact true, and sort of like analytic number theorists like work hard to kind of shave and shave and shave this error term and make delta bigger and bigger. So okay, so that's the first part of my talk where I say, what does analytic number theory mean to me? What does geometric mean? That's an even harder question. So let me just say, sort of, in some sense, the whole theme of like the first couple of lectures is going to be to explain what geometric means in this context. But for those of you who have heard of this, I'll just say that it is meant in the same sense as the geometric and geometric Langlands. That what we're going to do, to sort of give like a little sneak preview, is take these problems of number theory and transpose them into the setting of function fields over finite fields, and there we're going to find that there's algebraic geometry hidden inside the problem that was previously invisible. This is very much the situation of geometric Langlands, where people take ideas that come from number theory and sort of, in some sense, now it's kind of split off, and people do pure problems in geometry. They're sort of inspired by Langlands, and I guess some people even say it's physics. I don't know if that's true or not, but I've heard it said. No physics in my talks. So, in order to sort of get this idea across, I'm not going to start with the hard questions. I'm going to start with a question which, from the point of view of analytic number theory, is quite easy and classical. But I'm not going to let that stop me from recasting it as a somewhat difficult problem in a top cohomology. Why should I? So the theme of the first lecture is going to be sort of how to make easy questions hard. And then the rest of the lectures will be like ... and thereby learn something. Okay. But before I really jump into the question, I want to talk a little bit about this analogy between number fields and function fields, because that's sort of the crucial actor in everything I'm going to say. So this is a new part, which maybe requires a new Sharpie. So number fields and number fields and function fields, and let me sort of give like a standard definition. By a global field, I mean, I could give that an intrinsic definition, but I think I won't. I'm just going to sort of say what kind of thing a global field is either a number field, i.e. a finite extension of Q, or the function field of a curve over a finite field FQ, i.e. a field isomorphic to a finite extension of FQ parentheses T, the rational function field. So I said this in a slightly long-winded way, and there's actually a reason for this, which is important, so let me sort of take a moment to explain that. Why did I just say it's either a finite extension of Q or a finite extension of FQ parentheses T, which seems almost like what I said, except I expressed it in a syntactically more complicated way. The reason I did that is because, I mean, it's something that it's always worth having in mind in this game, in that if I have a number field, there's only one way that it's an extension of Q, so to speak. But if I have the function field of a curve, there are lots of maps from that curve to P1. There are lots of fields isomorphic to FQ parentheses T inside that field. I mean, it could be expressible as an extension of FQ parentheses T of different degrees, for instance. So you don't really want to think of, I mean, so in this game, I want to think of, I just want to say it's a function field that is isomorphic to some extension of FQ parentheses T, but I don't want to think of the inclusion of FQ parentheses T as part of the data of the field, and that's why I take the trouble to express it in this somewhat longer way. But I will say, by the way, that in most of the examples I do in these talks, the field is actually going to be FQ parentheses T, but I do want to emphasize that sort of nothing I say should be thought of as conceptually limited to that case. In fact, I think even today I'll say something about more general function fields. Maybe the last thing I say about more general function fields. So, on the face of it, these two classes of fields seem kind of different, right? One of them is characteristic 0, one of them is characteristic P, one of them has to do with number theory as we understand it, one seems to have more to do with algebraic geometry, but beneath the skin they're quite similar. And I sort of can't do better. Bjorn has a wonderful table in his course notes on rational points, which expresses a very, very, very long list of analogies between these two settings. I won't use all of those analogies here. I'll sort of like talk about some of them in the course of what I need. But it's a long-standing philosophy that that many of the arithmetic features of these two contexts are the same, and if something is true on one side, one has at least some reason to expect it to be true on the other. And in some sense, this whole talk will be within that philosophy. One other thing to say, of course, is that, well, let me say, so mostly here, so mostly we will consider, just to fix ideas, those two fields, the rational numbers and the rational function field, FQ parentheses T, except of course what you should then immediately object to is that, I mean, I didn't just write two fields there, right? FQ parentheses T has a parameter, I mean, there's one of those fields for each choice of finite field FQ. It's a real element, and so there's some long countable list of function fields. Hold that thought. That will be important in talks 2 and 3. But for the moment, you can just like imagine your favorite prime power and think of it as like one field that we're going to talk about. Okay, so let me begin to introduce some of the analogy and some of the entities that are on either side. So first of all, of course, most of the questions I asked in the beginning of the talk were not about rational numbers, they were about integers. So in other words, Q has this natural subring Z, and many of the questions we ask are really about Z. And so, analogously, sort of, FQ parentheses T has a subring of polynomials, FQ brackets T. I want to say a little bit more about that analogy because it's not quite precise. So let me comment that one way of thinking of what is this subring Z, this is sort of a somewhat perverse way to say it, but you could say it is the set of rational numbers such that their absolute value is less than or equal to 1 for all non-Archimedean, or let me say it like this, for all absolute value B, except the Archimedean absolute value, the real absolute value. So, I mean, integers, as you know, have a pretty big real absolute value, but p-adically, they're never too big, because to be big p-adically means you have some denominator of the power of p. So, these are elements of the field which are constrained, they're bounded by 1 in all absolute values except one absolute value, which is like allowed to just go hog wild. I mean, of course, you have to let one fly free, because if you bound all the absolute values by the product rule, you don't have anything interesting left. So, in some sense, like the most you can constrain absolute values is to constrain all of them above 1. And for function fields, it's the same way. So, analogously, FQ brackets T is a subring of the field FQ parentheses T, and this is the subring consisting of functions. Now, one of the absolute values here on this ring, you can take a function and you can see to what degree it vanishes and to what degree it has a pole at a point, at some value of T. And so, maybe actually, just because this might be a little bit less familiar, for each point P on the projective line, you have the absolute value of a function x at a point B is Q to the negative board P of x. I'm contracting this a little bit from what it says in my notes, which is why I hesitated here. I think this is like close enough for what I want to say. In the notes, I'll just comment that there's a little bit more to be said about the residue field of a point. So I'm being a little bit careless, but I just want to sort of give the idea. So this seems to work fine, except when I said, what do I mean by point of P1? Well, point of P1 is just the value of T, and so as you know, the projective line has all the sort of physical values, but there's also the point of infinity, which gives you an absolute value that looks a bit different. So I'll just comment that if x is a ratio of polynomials, P over Q, then the order at infinity of x is the degree of Q minus the degree of P. So what is our natural ring? Remember that Z is defined for all absolute values except for 1. It's not allowed to have any denominators. In the language of functions, we say it's not allowed to have any poles. So of the analogous subring of f cubed parentheses t is x such that the absolute value of x is less than or equal to 1 for all p except infinity, which is to say, if you remember that, if you look over at the definition, that's to say that the order at p is not negative, which is to say that there's no pole. That is, x has no denominator, i.e., I'm just going to write this in a lot of different way, i.e. x has no poles at values, so let me say it this way, x has no poles away from infinity, and this is precisely to say that x is a polynomial, capital P. So I apologize, I realize that I've used capital P to mean both a point on P1 and an unspecified polynomial. That's kind of bad, but so be it. It's done. It's being recorded. We can't change it. And then the absolute value of infinity is nothing other than, so now let's look back. I still have that definition up on the board. Then the order of infinity is, now there's no denominator, right? There's no q, so the degree of q is 0. So the order of infinity is negative deg p, which means that the absolute value is just q to the deg p. So indeed, this ring of polynomials is kind of a good stand-in for Z. It is precisely like a ring, a subring of the field consisting of all those elements of the field whose valuation at every place except 1, which we call infinity, is bounded by 1. And in infinity, the valuation, the absolute value is allowed to just like range freely. And indeed, you see that absolute integers, there's only finitely many of any given size, and they get pretty big. So that's the analogy we're going to have in mind, but there is a difference that I want to emphasize, which is that, so a difference in Q, infinity is special. It's the only Archimedean place. In f cubed parentheses t, in some sense, we can choose which point on P1 to call infinity. Like, God doesn't come down and give you, like, a special point of P1. I mean, P1 is like a very big group of automorphisms that act transitively on all the points, so we can choose any rational point and call infinity. So, infinity is not special. We can apply an automorphism of P1 to move it around, and in particular, I just want to sort of emphasize that, I'll give you an example, that I could take the ring of polynomials in 1 over 1 minus t, for instance, and this would be just as good of a subring of f cubed parentheses t as f cubed brackets t. I mean, indeed, there would be like an isomorphism, there would be an automorphism of the field sending one ring to the other. So that's the difference, that somehow in Q we have this canonical ring of integers. Here, involves making a choice. Having said that, I'm going to make that choice, and we're just going to like always talk about f cubed brackets t, but I want to emphasize that it's somehow less canonical, and that maybe a way to think about this is that in the function field case, you see, I mean, you guys probably know that in the number field case, there's lots of analogies where you say, oh, I expect something that happens p-adically to be analogous to something that happens Archimedeanly, right? Something that happens with respect to the prime p being analogous to some phenomenon that happens with respect to the prime infinity. And in the function field case, those are more than just analogies because those are literally, so to speak, the same kind of prime. There's nothing special about the prime infinity. Okay. So, with this choice of something in place, hey, remember, when did it actually start, by the way? I realized I forgot to check when. So I started at 30 and I'm going to 20? Okay, perfect. So with this analogy in place, let me sort of get a few more things set up. For instance, in Z, we often are going to talk just about positive integers. And so one way to think of that as the positive integers are coset representatives for Z mod Z star, which is just plus or minus 1, right? I mean, I want to have one representative for each class of multiplication by units, and I can do that by just looking at positive integers. And the analogy over the function field side, so maybe I'll use this little symbol to be an analogy, would be monic polynomials, which are coset representatives for F Q bracket C mod the units in F Q bracket C. Of course, those units are just FQ stars, just multiplied by constants, and if I want to eliminate that ambiguity, I can do so by forcing my polynomials to be monic. So whenever we're talking about positive integers, on the number field side, we're probably going to be talking about monic polynomials on the function field side. Similarly, another thing we're going to talk about a lot on the number field side is intervals, right? Almost all of the questions I asked had in mind some interval of integers. That may at first seem like something that would be hard to analogize in the function field setting, because when we talk about an interval, it seems like we're talking about the ordering on the integers, starting here, going to there. And of course, the polynomials don't come in any particular order. But that's okay. I mean, there's a different way to think of what an interval is. I mean, after all, an interval in Z can be thought of as the set of n such that it's at the absolute value of its distance from some fixed n0 is less than or equal to some other constant d. Right? I mean, that cuts out an interval, saying everything within d of some other integer n0 at the center. And similarly, what we mean by an interval, because the notion of absolute value carries over very nicely, so it makes perfect sense to say an interval in F Q bracket C is some set of f such that f minus some fixed guy is less than or equal to some size. Maybe I don't actually want to use d for this, maybe I'll say e. But remember that this equals q to the degree of f minus f0. So what you're saying is that an interval is you fix some polynomial at the center of your interval, and you're going to say it's everything that differs from that by a polynomial of small degree. And that's the natural, analog. In particular, the one we're going to use all the time is e.g. f such that the difference between f and x to the n is less than or equal to q to the n minus 1. What is that? That's the set of all polynomials whose difference from x to the n is a polynomial of degree of most x to the n minus 1, which is precisely to say it's a monic polynomial of degree n. So that's sort of a very natural interval in the function field setting, and like a lot of the theorems we prove, that's going to be the interval we choose to work with. So equals monic polynomials of degree n. And of course, I mean, as I change n, like this is a partition of all monic polynomials, and so these are kind of going to be the intervals on which we do most of our questions. Okay. So I think those things having been said, I can start talking about the first question of analytic number theory that I want to analogize and show you now how I sort of cart over using the wheelbarrow we just built all the ideas and insights from the number theory, from the number field side to the function field side. So But that's a simple question. So now we're going to talk about square-free integers and square-free polynomials. So the question is this. How many integers in the interval from n to 2n are square-free? So this is a classical question of analytic number theory, much like the question I asked at the beginning about the probability that two random integers in a box are co-prime. In fact, this sort of has the same answer as that question, although it's not literally the same question. How do we think about this? I'll sort of quickly recap. So one might expect the probability of square freeness to be described as follows. Well, to be square free, first of all, is to be not divisible by 4, right? So take a random integer in a large box, and there's a 3/4 chance of that happening. So 1 minus 1/4 of the time, you're relatively fine, but you don't contain a multiple of 4. Of course, you also want to not be a multiple of 9. So 1 minus 1/9 of the time, you're not a multiple of 9. You don't want to be a multiple of 16, but that's completely redundant, right? Because you've already stripped out all the multiples of 4 in this sort of primitive sieve that we're doing here, so you don't have to even say that. But you do have to assert that you're not a multiple of 25, and so you get a new thing. And of course, you can see what we're doing here. This process is going to end up giving us an infinite product over all primes of 1 minus 1 over p squared. Now, by the way, what I just did is completely unjustified. I mean, this is why I wrote one might expect. I mean, somehow embedded in this infinite product I'm writing down is that we expect all of these infinitely many conditions to sort of somehow be probabilistically independent, or at least probabilistically independent enough as the size of the box grows larger, that this statement is actually correct. It's not my business in this set of talks to explain why that is okay, but it is okay. So let me just say that, and indeed, this is so. Namely, I'm going to give this, I'm going to have to refer to this quantity a lot, so let me give it a name. SF of n, square frees, is the number of square frees in the interval n through 2n, then it is the case that the limit as n goes to infinity of n negative 1 number of square frees of n. So this quantity that we're taking the limit of is some probability that depends on n. The probability that the integer in this box is square free. And that does indeed go to this infinite product over all primes, 1 minus p to the negative 2. Of course, this is also known as an inverse special value of the zeta function, of the Riemann zeta function, evaluated at 2. And this one I noticed I wrote it correctly in my notes. I did not write zeta of 2. So I guess this is the point where that convention runs out when I write probabilities that are less than 1 in my notes. And what's more, by the way, I think I won't write this up, but this is also known to be true with the power-saving error term, and again, people sort of like work hard to sort of shave down that error term as small as they can. But what I want to talk about in sort of our closing minutes today is just to give a picture of what this problem looks like over FQ brackets T. And of course, our experience should lead us to believe that in some sense, the problem will be the same. And that's very much true. Let me show you how this works. So over FQ brackets T, yeah. How's that? Okay. So we're going to translate everything. Our interval, as I just mentioned, the interval that I'm going to use, but what's my I got to sort of find some way of making bigger and bigger intervals, and my natural way to do that is the way I just said, that our interval is going to be monic polynomials of degree n. So this is the form xn plus a1x to the n minus 1 plus dot 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 plus an. And similarly, I have to draw a line between capital N in the previous slide and little n now. And what I want you to know is that the size of this interval, how many polynomials are in there, well, there's n coefficients to choose. So this is an interval of size, where by size this means like number of dudes who are in there, an interval of size q to the n. So we should think of q to the little n as going with big N. So I mean, we're using the kind of usual convention where small letters exponentiated become capital letters. Okay. So have we said everything we needed to say? Yeah. So good. So what this tells us, before we asked what is, so let's write SF sub q of n equals number of monic square free polys of degree n. So the number of square free guys in our interval, same question, and now we can ask about the same limit. So what is the limit, and now as n goes to infinity, of 1 over the size of the box, which is now q to the minus n, that's the analog of capital N to the minus 1, times the number of square frees in the interval. And this is a question to which one knows the answer, so I'm going to cross out what is. And write the answer. And the comment I want to make is that just as I promised, the answer is the same. It doesn't look exactly the same. I mean, if you look at that, it doesn't look like 6 over pi squared, but it kind of is. They're both less than 1, but that's not why. And the reason is that, of course, another way to write this, I mean, I just sort of told you some answer and it kind of came out of the blue, and I won't do it today, but next time I'll prove to you that this answer is correct. I think it's good that I prove something at some point. But heuristically, following the exact same argument that we did before, we might have expected that this limit should be an infinite product, just like before. One thing I didn't say, but I'll bet you can guess, is what's the analog of a prime number? Well, a prime number should go with an irreducible polynomial, right? The definition is like exactly the same. So let's have a product over, P irreducible. And now, it should be the same thing. What is if P is a polynomial, an irreducible polynomial, what's the probability that a randomly chosen polynomial is divisible by the square of that polynomial? The probability that I'm divisible by some given linear polynomial is like 1 over q. Because that's saying if I evaluated that point, I get 0 out of the q things I could get. And similarly, it's not hard to check that the probability that I'm divisible by some chosen polynomial of degree k is q to the minus k. So one way to write this is 1 minus q to the, but now I have to check whether I'm divisible by the square of that linear polynomial, and that's a probability of 1 over q squared. So it's really 1 minus q to the negative twice deg p. But of course, yes. So p irreducible mod. But you know, it's kind of like when you say primes, do you say positive primes? I mean, if you look at the definition, I just taught this to my freshmen, so I'm keenly aware that this is the problem with the definition. You don't ever say it, right? You just say, oh, in terms of the factors, and then some guy in the back, right? Always. I teach to a group of freshmen about the same size. Somebody's going to bring it up. Anyways, it's similar, yeah, there's probably going to be some point at which I stop saying monic, but I always mean it. Non-monic polynomials are banished from my tongue. Okay, anyway, but of course, I've given you this absolute value. We should use it. So another way to write this is the product over all p. And now I'm just going to write p, because, damn it, if you write a product over p, you mean primes. When you mean primes, you mean irreducible. So you don't even, you shouldn't even have to say it. 1 minus the absolute value of p to the minus 2. And of course, as you guys know, if you guys do Dedekind zeta functions or any zeta function like more general than the plain vanilla Riemann zeta function, you're always sort of taking the norms of your primes, right? So even when you write the regular zeta function, you write 1 minus p to the minus 2, or 1 minus p to the minus s. In my opinion, you should write 1 minus the absolute value of p to the minus s. Because morally speaking, it's the real number you're multiplying, not the integer whose absolute value is that real number. Is that pedantic enough for you? And yet, you see that here, you sort of have to do it this way, right? You can't multiply together the primes are the characteristic p things, right? You can't multiply together these irreducible polynomials and get like a complex function. You have, so you have to do this. Anyway, the point is that this is, by definition, again, a special value of the zeta function. So this is, by definition, but now the zeta function not of the ring Z, but the zeta function of the ring F brackets T, evaluated it to the minus 1. So now you see why I said, so maybe there's one more step I should say, that in fact, here a great miracle happens, which is that this giant infinite product over irreducible polynomials, if you actually sort of like revved up your computer and started multiplying them, you would see something rather amazing, which is that, as you might hope, so this equals 1 minus 1 over q. So here, somehow, I want there to be like a massive bouquet of exclamation points around this equal sign, because that's not supposed to be obvious. That's like some great fact that, again, there are somehow many moments we can split off into sort of some long, beautiful story that if I were giving a graduate course, I would spend a lecture telling, but I'm not going to tell the story of zeta functions of curves over finite fields. I'll just comment and interpret it that way. This infinite product does evaluate to this, and that sort of justifies this statement. Again, I'll comment that you could, if you were an analytic number theorist, you could make a proof that was completely uniform, bounding error terms, and showing that the heuristic infinite product was correct. In both cases, no problem. It wouldn't even be too hard. So next time, I will actually prove that this limit exists and is equal to 1 minus 1 over q in a totally different way. And I will, so one thing I haven't done yet is say a single word that I would call geometric. I'll do that next time. Okay, so thanks very much.